Good morning, one and all. Today we are going to discuss about some of the topics in strength of materials. So my name is Dr. Y.Carlin Calph. I'm Assistant Professor in Department of Mechanical Engineering. So in this time we are going to discuss about the strength of materials basics like stress, strains, etc. Some of the topics which are very valuable for us. So first the topic is the strength of materials. Why we are going for this strength of materials? So to know about the materials, various materials, their stresses and strains, and also structural members such as beams, columns and shaft. So the method employed to predict the response of a structure and loading and its state to various failure modes. So the failure modes of a material or a metal, the failure mode will happen in yield strength, ultimate strength and Young's modulus and Poisson's ratios. So in addition, the mechanical elements, geometric properties such as its length, width, thickness, boundary constraints and some unexpected changes in geometry. So these are some of the criteria we are going to analyze. So the components yield strength, ultimate strength, and also we are going to learn about the length, width, thickness, boundary constraints of the materials. So first of all, before knowing the details of the material, we have to analyze about the properties of materials. To finalize the material for an engineering product applications, so it is very important to understand about the properties of the materials. So the mechanical properties of material, those which affect the mechanical strength and ability of a material to be molded in suitable shape. Some of the typical mechanical properties of a material includes strength, toughness, hardness, hardenability and brittleness, malleability, ductility, creep and slip, resilience and fatigue. So the strength is the ability of a material to resist the applied load without failure. So when we give the load to the component, so it should resist the applied load without failure. That is known as the strength. The capacity to resist the load. So this is one of the important properties of constructing beams or any of the load supporting columns. And also materials which we finalize for our engineering products must have suitable mechanical strength to be capable to work under different mechanical forces or loads. So the products or the materials which you are going to select should have these capabilities, that is mechanical strength at different forces and different loads. So when we give different loads to the materials, so they should resist that load. And if they should be capable of maintaining that load, and they must not break or rupture. So this strength is very important for the materials or metals. So ultimate strength refers to the maximum force needed to fracture the metals. So metal, we are giving some strength to the materials, and you are giving the maximum strength to the materials. So the maximum strength is very important. The maximum strength means the forces, the maximum force before the rupture or before the breakdown you are giving, that is ultimate strength. So then only when you give the ultimate strength to the materials, so the material should be resistant and it should be supportive, and it should hold that load without fracture. So that is, so most of the components in the engineering, in the strength of materials, they need ultimate strength. So in the engineering applications, right? The property toughness, the property of metal which enable it to be twisted, bent or stretched under a sudden impact before rupture. This property is essentially required for steel when used as rails and carriage springs. So the toughness is one of the properties which enable it to twist, bend. So when you take about the solid shaft or solid pipelines, it can be twisted. So the twisting effect, so it can be twisted and made to some applications, and it is bent or stretched under sudden impact before ruptures. Okay, the load will be suddenly given to the components. That is very important. That is known as, the load is known as impact load. So when you give the impact load to the materials, the material will go for some deformations. So the twisting effect of a bar, or to make a bend of a bar, or the stretchment of the materials. So this is very important, toughness. The property is essentially required for steel when used as rails and carriage springs. So the application is most of the steels they are using for rails. So the rail should have it should hold the load, and it should resist the load, and carriage springs. So most of the we will be using the springs. The springs will be very supportive. Say they have to hold the toughness with themselves. So rails and carriage springs are very important in toughness. So hardness, the property of metal that enable it to resist penetration, indentation or abrasion by other materials. Cast iron when used as lathe bed has this property, right? Okay, see, when you go for the hardness, the indentation property of the materials, each and every layer, each and every atoms of the materials should be very hard, and it should resist the penetrations. When you hold, or when you insert some pin or scratches, or when you give some load on that hard material, it will resist. So that is one of the properties. This hardness has got some many properties. The hardness number is there, and the hardness number increases, the hardness increases. Okay, so the atoms are very tightly bound, so they don't have any vacuum, any gap in them. So like that, atoms are very useful for penetrations. The indentation properties, penetration and indentation properties, these both are very important in the hardness. And abrasion by other material. So the abrasion is very important. Yes. So the abrasion will make the materials to reduce, okay, or to remove some of the materials from the surfaces. So to be hard, so the materials, the particles should be bound very well, and also they should be very hard. The atom should be very hard, and they should have high bonding, cohesive bonding strength. So this makes them very hardness. Okay, and cast iron when used as lathe bed has this property. So cast iron was used in lathe bed, and also the surface of the cast iron is heat treated, and the upper surface always will be very hard. And also when you move bed in the carriage in the bed, and also in the moving devices or moving carriages, when passed into the lathe bed, so they are not even abrasion, and also they are being very hard. So this is one of the property of the cast irons. So the upper surface or the outer surface can be hardened, so that is very important, and also the outer surface should not deform, so that is very important. The cast iron when used as lathe bed has these properties. So wear resistance is a property of metal associated with the property of hardness. So it is associated with, they should have that wear resistance in them. Okay, the wear resistance is, so it should not wear. So when you take about the cutting tools or coated cutting tools or cutting tool inserts, so when it is when the machine under machining conditions, the wear will be very less. So some of the coated inserts or the cutting tools with high hardness, they are very wear resistant. So on machining the components, their wearing is very less. So the wear property of the cutting tool inserts or the surface of the bed should be reduced. So hardness is one of the best properties. So increase the hardness. So they will add cobalt or tungsten carbide like materials. So the cobalt will be a high bonding strength, and also the tungsten carbide materials will have high wear resistance. So mostly they are using for the cutting tool instead, and also HSS steels also. In the olden days they used the HSS steels, but now due to the wear resistance, we are using the cutting tool inserts for manufacturing the components. So now due to the wear resistance, we need a combination of materials. The combination of material will be used for it, and by using the titanium, tungsten, aluminum or carbide, cobalt and chromium. So the chromium also will have high wear resistance. And scratch hardness. In the when you go for the hardness, we have got another property, that is scratch hardness. The ability of material to oppose the scratches to outer surface layer due to external force. So when there is happen when two materials they go among one another in opposite directions, so they need to be there should be scratch resistance. Okay, the scratches should be the outer layer of the scratches should be controlled. So when external forces applied to that material, the scratches will be very reduced. Okay, and the ability of material, the opposite scratches. So the minimum scratches in the outer surfaces gives the outer surfaces with minimum scratches. The surface will be very good when external forces applied. What are the force applied to the outer surface? So it should be scratch resistance. Most of the cast iron beds or hardened bedways will be scratch resistance. In the CNC lathe we use more bedways, and also the lead screws and everything. Whatever the surfaces are used in the outer surface, they should have scratch resistance. And the indentation hardness, the ability of material to oppose the dent due to punch of external hard and sharp objects. Okay, that is indentation properties. So when we enter a sharp object into the hard components, it must not enter. It should tend to opposite. Okay, that is the external surface should be very hard. The external surface is very hard, and when we dip or when we press about on keeping a punch or any other materials on the components, so it must not enter into it. That is known as the indentation properties. Okay, so sharp objects or sharp pins or any of the sharp materials, sharp needles. So when you scratch on that area, the external area should be that is opposed to that. So the scratch resistance. So that is known as the indentation properties and indentation hardness. The indentation, it should not, the sharp objects on the external material, it should not enter, and it should tend to oppose. And rebound hardness. So it is also called as dynamic hardness, that is lively hardness. Okay, when you take that determined by height of bounds of a diamond-tipped hammer. So there is a diamond-tipped hammer. So the hammer will be forced will fall from a upper end to a bottom. So then that should resist that hardness. That is rebound hardness. Okay, it is also called as dynamic hardness. It is determined by the height of bounds of a diamond-tipped hammer dropped from a fixed height on the material. So a diamond harder, the diamond is very hard. It is dropped from a fixed height on the materials. Okay, that will rebound. And how the hardness is? So how the hardness of the material is. So that we are going to calculate. Okay, the base materials are kept and the diamond is very fallen through the hammer to the materials. And if it is, when it is rebound, what happened on the materials? If it is, there happens some fracture or rupture on the materials, or the material is very polished. So that is known as, we say, as rebound hardness. So hardenability, the ability of a material to attain the hardness by heat treatment process. It is determined by the depth up to which the material becomes hard. So due to heat treatment, the surface becomes hard. The material's hardness increases. So some depth it will go. The depth of the materials, that depth is known as the hardenability area. It is determined by the depth up to which the material becomes hard. Up to which area, up to what the depth material becomes hard. So this is known as hardenability. And brittleness of a material indicates that how easily it gets fractured when it is subject to a force or load. That if you take glass or ammonia, any materials, that will have the brittleness properties. Okay, so when it is put down, that will become this brittleness. So it can easily fracture when it is subject to a force or load. When a heavy load is given to a material, or when a heavy or light load is given to the material, easily that material fractures. So this indicates as brittleness. When a brittle material is subject to a stress, it absorbs very less energy and gets fractured without significant strain. So absorbs very less energy. So the energy is not stored. That the energy is distributed like that. When a brittle materials is when the stress is given to the materials, so by the less energy also it gets fractures without any significant strains. So there won't affect any strains. Some metals which are ductile at normal temperature become brittle at low temperatures. Okay, at normal temperatures, some materials will be ductile. So at low temperature, the material tends to be as at brittle. So the property of solid material, which indicates that how easily a material gets deformed under compressive stress. So this is malleability. So how easily it can deform under compressive stress? When there is given a compressance, so that will be as it has got the malleabilities. Malleability is often categorized by the ability of material to be formed in the form of thin sheets by hammering or rolling. This mechanical property is an aspect of plasticity of materials. Okay. So making thin sheets. So when we have the thick sheets and two rollers are there, when you press the sheets, so they will become as thin sheets. Okay, this materials due to the high compression, that is compressive stresses. So when the thin sheet is thick sheet is compressed, that will become thin sheets. So formed in form of a thin sheet by hammering or rollings. When hammering or rolling, the sheets become very thin sheets. Okay, this mechanical property is an aspect of plasticity of material. This is also an aspect of plasticity of materials. Okay, because the deformation takes place, the thick sheets will become as thin sheets due to hammering or rollings. So most of the sheet metal sheets are used in this way. Most of the sheet metals. So when in the high compressions, the material thickness will be reduced to thin sheets. Okay, so thin sheets manufacturing is very important. So the property of malleability is applied in thin sheets. So ductility. So the property of a solid material, which indicates that how easily a material gets deformed under tensile loads. So when two opposite loads act on the materials, you will get the ductilities. So ductility is often categorized by ability of material to get stretched into a wire by pulling or drawing. With rise in temperature, the ductility of material increases. With rise in temperature, the ductility of material increases. Okay, so this is a property of a material to making wire by pulling or drawings. When you pull, the wire will be increased. The length of the wire will be increased. The diameter of the wire will be decreased. This is one of the important property of making electrical wires are small, that is thin wires, thin metal wires. Okay, so when we give equal pull to the materials, so by pulling or drawing, so they will tend to get stretched as a wire. So the property of a solid materials, so the deformation takes place in the opposite directions by pulling or drawing. So this properties makes of manufacturing wires. Creep and slip. The property of a material which indicates the tendency of material to move slowly and deform permanently under the influence of external mechanical stress. The tendency of material move slowly and deform permanently. Okay, the tendency of a material to move slowly and deform permanently under the external mechanical stresses. Okay, the material will move slow, and also it will be slowly, and the permanent deformation takes place. So that is known as creep. Creep is more severe material that are subject to heat for a long time. So when the material is subject to heat for very long time, so daily some of the deformations takes place due to heat, and the deformation will be very slow, but it will be permanent day by day. So hence creep is more severe in materials. So due to creep, most of the hot working atmosphere materials, hot environment materials, so will go slowly and deform. Slip in material is explained with high density of atoms. The high density of atoms will go from one area to another like a plane. Okay, the shifting of planes. This plane is known as shift. So the density with high density of atoms, okay, will be shifted, and also there happens some slips on the materials. So the ability of material to absorb energy when it is deformed elastically by applying stress and release the energy when stress is removed. So the absorbers of energy. Okay, by applying that load. So when stress is applied to the materials, so that that will be deformed elastically. Then also that will absorb the energy. Okay, the ability of material to absorb the energy when it is deformed elastically by applying stress. Okay, and they release the energy when stress is removed. This is known as resonance. It is the storage of energy. Proof resonance is defined as the maximum energy that can absorb without permanent deformations. Okay, so this is known as that is maximum energy that can absorb without permanent deformations. It won't differ, and also that will be in the good conditions. When you give the load, okay, that will absorb energy, and when maximum energy is applied, that will absorb the energy and it won't deform. So this is known as resilience, proof resilience. Fatigue. So weakening of material caused by repeated loading of the materials. When repeated load is given to the materials, so that will become weakening. Okay, that is known as fatigue. So weakening means the strength will be reduced, and also the unavailability of doing that work again and again. That is weakening of materials by the repeated loading. When a material is subject to cyclic loading and loading greater than certain threshold value but much below the strength of material, microscopic cracks begin to form grain boundaries and interfaces. Okay, so when cyclic loading, repeating cyclic loadings, this is known as a certain period of time loading unloading that will be going on to the materials, so below the strength of material, but there will happen some microscopic cracks, that small atoms cracks or small grain boundary cracks will be happen here. So there will happen some interfaces, okay, due to the interfaces. So and also this micro cracks will begins, and also will make some problem on the materials. So that is known as fatigue. Okay, the strength of material, micro cracks begin to form a grain boundaries and interfaces. So stress. So we have seen the mechanical properties of the materials. So different materials will have different properties. From the strength, strength is the strength, and also we have seen malleability, ductility, and many properties. Now we are going for the simple stresses and strains. Okay, so when we apply the load, what will happen to the materials or metals? So that we says we are going to drill here. First one is stress. The force of resistance per unit area offered by a body against deformation is known as stress. Stress is equal to load by area. So when load is applied to a materials, so that should resist the load. That is known as stress. So stress is known as sigma load by area. That is P by A. Stress is equal to Newton by mm square. Area is equal to denoted as mm square. Right. Strain. When a body is subjected to some external force, there is some changes of dimensions of the body. So when the external force is applied to the material, the dimension, there will be some change in dimensions. Increase in length will be there, or increase in thickness, diameter. What will be the ratio of change in dimension to the original dimensions of the body is known as strain. So the ratio of change in dimension to the original dimensions, that is known as strain. The strain is dimensionless. There is no dimension because that is the ratio. Okay. So the strain means, suppose if a bar is 100 mm length, so when we give load to the level some increase in 0.1. So the 0.1 is the increment. So that is known as the change in dimensions. Okay, that we say as L is equal to 100 mm, delta L is equal to 0.1 mm or 0.0456 like that. So the change in length will be very less change in dimensions. And stress units, so that is Newton per meter square or Newton per mm square we say it as, or Pascal, mostly we are using Newton per mm square. So by the unit 1 megapascal is equal to 10 power 6 Pascal, 1 gigapascal is equal to 10 power 9 Pascal, 1 kilopascal is 10 cube pascals. So these are the some dimensions we are going to convert the units. So mega means 10 power 6, giga 10 power 9, and kilo 10 cube. So the types of stresses, that is tensile stress, compressive stress, shear stress, bending stress, and torsional stresses. So these are some of the type of stresses. So tensile stress, the stress induced a body when subjected to two equal and opposite pull, as a result of which there is an increase in length, is known as tensile stress. So there is some increase in length. So this is a body here, and also two equal and opposite, so pulls are there. This is one pull and this is one pull, so they'll be acting to opposite pulls. And also this material tends to elongate. This will tend to elongate. Okay, this is known as tensile stress. So the elongation will be carried on. And compressive stress, the stress induced the body when subjected to two equal and opposite pushes, as a result of which there is a decrease in length of the body, is known as compressive stress. So two opposite and equal forces inward, it acts inward, that will push the body, so that will the length will be decreased. Okay, decrease in length. Okay, this is known as compressive stress. So this area will be reduced. If it is the radius 100, that will be reduced here. So this is known as the compressive stress. So next we go for the shear stress. Shear stress is the resistance to deform due to perpendicular forces operating along the surface. In the surface area, the forces will be acting here. Okay, they acting. So that is known as shear. So when the welding is attached, or when you go for some welding will be there, when it's attached to opposite direction, two forces acts here. So that will form as shear will be there. Mostly we go for rivet. So when two sheets are joined by riveted, when forces acts opposite, so there starts with shear. The shear is the angle of shear is theta. So the shear will be acting upon the surfaces. Okay, to deform due to perpendicular force operating along with the surfaces. Okay, sometimes the opposite forces will be acting, so then it will crack down. And bending stress. So bending stress is the resistance of an object to bend. In bending, the force is the normal load and applied at a specific spot of the object. Okay. So some spots where the bending is given, the bending stress is given here. This is load here, and some bending stress is given. So that when bending is given, this bending load is given to it, so that will deform it, that will bend. And in bending, the force is normal load and applied at a specific spot of the object. Okay, the load is very normal. You are applying the load here, then it will bend it down. So you will get some deformation in this material, some change in the angle here. So that is known as bend. So this bending stress is very, very important. So in the manufacturing of steels, and you get the design. And that is torsional stress. This is known as the twisting effect. The torsional stress is shear stress caused due to twistings. So due to there happens some twisting in it. So this torsion material is simply twistings, angular deformation of a body. So there happens some angular deformation of a body. This is known as twist. The twisting effect is known as the torsional stresses. And also that will change in the angle. This angle will be changed here. Okay, so due to this, when we fix in a solid in the chuck, when we fit the shield rod, and it will be twisted. Okay, there will happen some angle in the rod, so that will tend to torsional stresses. And we go for strain. So the ratio between change in length to the original length. So we go for the formula. The strain is equal to delta L by L. So this is E is equal to compressive or tensile strain. We go for change in length. Delta is change in length. L is meant by the original length. So strain is deformation produced by stress. Strain is deformation per unit length. So measure the linear strain. Strain processes are used to measure the linear strain. So this strain is measuring gauges. They are used for measuring the linear strains. So the linear strain, the deformation of bar unit length, the direction of applied load. So this is known as the linear strain. Change in length by original length. Due to the length, change in length, we get the linear strain. Lateral strain. So to the direction of the applied force, bar per unit. In the deformation of the bar per unit length, in a direction right angle to the direction of applied load. So lateral strain mostly happen in the diameter. change the diameter to the original diameter or change the length to the original length. And shear strain means the shear strain due to angle. So angle through which the body distorts, that is known as I tan psi is equal to, you get this. When a square or rectangle box subject to shear force is in equilibrium, the shear stress is one plane is always associated with the complementary shear stress of equal magnitude in the other plane at right angles too. Okay, this is means we are going some angles is equal to E of shear is equal to, that is you get these some angles here. Volumetric strain, that is change in volume by the original volume. So this is very important. Okay, the change in volume of a body to the original volume, that is known as the volumetric strain. So next we go for the modulus of rigidity, that is shear stress to shear strain. So by stop. So most of defined as the shear stress to shear stress, it is denoted G, C or N. This is called shear modulus or modulus of rigidity. So this is known as G is equal to shear stress by shear strain. That is bulk modulus, that is volumetric stress by volumetric strain. This volumetric stress V by EV is known as the volumetric, that is bulk modulus K. That is you get the volumetric stress value, and when it is divided by volumetric strain, you get the bulk modulus. Elongation of a bar. Elongation of a bar is delta L is equal to PL by AE. So this is known as the, when you go for this, the delta L is, you get the change in length. P means load, pull. So that load in newtons or kilonewton. L is equal to length of the rod, the length of the rod in millimeters. So area, if the circular shaft, if it is a circle, pi d square by 4, and you are getting mm square, and E is equals to Young's modulus, that is 2 into 10 power 5 Newton by mm square. So these are very, very important. You can change it. If suppose if you want to find the change in length or change in length of a bar, it is known as PL by AE. Suppose if I want to get the Young's modulus, PL by A delta L, the E will become, you can interchange it. So if we can get the values here, known values from unknown, if delta L is unknown, you can get it, or E is unknown, you can get it. That PL length also is there. So basically most of the problems, delta L, change in length also E, the Young's modulus can be found by these methods. So elongation of a circular tapered bar. So why the tapered bar is there? That is, if it is, why the tapered bar D1, the diameter will be differentiated. Okay, that so that if you go, that is PL by D square by 4 here. So D square D1 D2, because it's a tapered bar. So tapered bar, the D1 D2 is here. So the diameter will be varying. So due to the circular tapered bar, so the D1 may be small or D2 will be larger, or some different may be here. And it's E is equal to Young's modulus. So delta is equal to 4 PL, that is 4. P means load, the load applied, and length of the rod. So D1, D2 to diameters, Young's modulus. By this you can find the elongation of circular tapered bars. That P is applied load, L is length of the bar, and E cross-sectional area, E modulus of elasticity of the material of the bar, and D1 D2 diameter at the end of the bars. Okay, the both ends will be there. So these diameters are very, very important. So these diameters that you can put the values here, and also this by D square by 4, the formula is slightly modified, D square D1 D2s, and by this you can get the delta value of delta L. Suppose you can get the Young's modulus, you can interchange it and you can get the Young's modulus values. So next, Poisson's ratio. So defined as the lateral strain to the longitudinal strain is known as the Poisson's ratio. Mostly the mu or 1 by m. So mu or 1 by m mostly we are using here. Okay, that mu 1 by m is equal to mu. Mostly we will say it. That lateral strain, what is that? Is transverse strain. Lateral means change in diameter by original diameter, change in thickness by original thickness, change in width by original width. That we say as the lateral strains. And the longitudinal strain means change in length by original length is known as the longitudinal strains. So these values, the m values varies from 3 and 4 for different materials. Okay, for most metals, mu's vary from 0.25 to 0.35. So this will be varying from 0.35 to 0.25 to 0.35. So mu, that is 1 by m, the Poisson's ratio for giving most of the materials when you go is 0.25 to 0.35. So the cork, it is 0.0, glass 0.02 to 0.03, beryllium 0.08. These are very reduced, and concrete 0.1 to 0.2. This is the value of Poisson's ratio. Most of the iron, cast iron, wrought iron steel, wrought iron stainless steels, so these will be 0.2 and 0.3, 0.4. So these are 0.2 to 0.3. Most of the metals or most of the materials will have the Poisson's ratios 0.25 to 0.33. So mostly it may go to 0.4 also, when that is for gold and lead 0.4. Re-entrant foam is minus 0.7. That is the foam. So this is entered a different here, but most of the materials we go here from cast iron to the lead. So that will be 0.222 or 0.44. Most of the year. But when they ask the questions, we can take the constant value as 0.25 to 0.35 Poisson's ratios. But here, according to this materials, this values, we can get 0.27 to 0.44. Right. See, the Poisson ratio is a very important property of isotropic elastic materials. The range is -1.5. So incompressible clay, paraffin, rubber, mu will be 0.5, and the ideal elastic incompressible materials, the volumetric size is 0. For a perfect rigid material, mu is 0.5. Then stretching a bismuth causes no lateral contractions. Okay, this may be 0.5. Perfect rigid materials. So mostly we are going for 0.5. Okay, for a perfect isotropic elastic material, Poisson ratio is 0.25. Okay, that is polymers will have negative values Poisson's ratio. So isotropic metals have a more Poisson's ratio of 0.5 in some directions. So we go Poisson's ratio isotropic and non anisotropic concept. Some bizarre materials have mu is less than 0. Okay, so some different materials are there. By this graph you can say this re-entrant form is entirely different, and also cork, glass, beryllium, concrete will be different. But these cast iron materials or some of the metal materials will have same Poisson's ratio. Next, the stress strain behavior of materials. Okay, to measure the stress strain behavior of the materials, we are going for one test that is known as the simple tension test for mild steel specimen. Okay, most of the mortar shafts or any other material shafts, we are using mild steels. So one of the basic concepts is mild steels is one of the major material application industries. So by using the mild steels, we are doing the tensile test by using the universal testing machines. Okay, so these machines will be there. Here we'll have the load cell, and also this is holding grips will be there, and the specimen is kept here. So by this moving this cross slate, so that it will tend to deform. Okay, like a rubber. The steel can be, one will be in the holding positions, constant positions, so another will be moving. By this you can find the values here. What are the values here? You can find the cross heads will be moving upward. And the load applied on dial and the extension initial stages measured using an extensometer fixed on specimen self, and later stages by scale fixed on machines. So to measure here, the component is fitted, and by using the dial indicator, that is the extensometer, okay, dial and the extensometer, you are going to measure. All machines are provided with autographic recorder, which is directly. So there is an autographic recorder, it is there, load versus deformation curve, stress strain. So to fix the extension on specimen, 2 points are marked on a portion of specimen. The distance between these points over which the extension is marked is called gauge length. So we're taking that components, and you are setting on major areas in 2 points. So that distance is known as the gauge length. Okay, on the other position. So to fix the extensometer, they are marking 2 points and fitting the extensometer and getting the values here. What are the values we need here? As stress, strain values, and the deformation values. And we go for that. This is known as the stress strain, that is diagram. That is stress strain diagram will be there. So for mildest shear, the curve is like this. We will have points P, E, Y1, Y2, U and P. The P is known as the proportional limit and E is elastic limit, Y upper yield point and Y to lower yield points, and U ultimate stresses and B for breaking points. So that is in this point, this O into P, that is the stress is linearly proportional strain. At this stages, the stress is proportional to linear proportional strain, or the stress is proportional strains. So in this their own deformations takes place here. That is the stress is proportional strain. In elasticity between P and E is not linearly. So this P and E, that is not linear. Okay. So that won't be in the linear conditions. In upper yield, the point on which dislocation breaks through interstitial carbons, atoms and lateral strains, the phenomenon is particular to mitral steels. Okay, the dislocation takes place, that is upper yield point, due to the interstitial carbon atoms dislocations. So dislocation means the atoms will be dislocated at this stage. Okay, at this stage, stress is proportional strains. Here it is, this is non-linear condition. Here it is linear. It is in straight line. But this point P to here it is non-linear conditions. Because some curve is there, some small deformation is there. But in Y1 point, this interstitial carbon atoms, some dislocations takes place at this point. This takes place at this point. And relief lateral strains. This phenomenon is particular to mitral steels. This is very particular to the mitral steels. And lower yield points. So here requires this that is lower stress is given here at Y2 point, that is lower yield point 2. Here we give more force, and here that force is the stress is very low. When carbon atoms are overcome by the dislocations, relatively lower stresses are required to keep the dislocations moving. This happens on Y2, right? Okay, this is known as the lower yield point here. Once carbon atoms are overcome by the dislocations, relatively lower stress are required to keep the dislocation moving. This lower stress is applied here. So this is ultimate stress. Maximum stress in a tensor is reached at this point. This is the main point. Maximum stress is reached here. This is ultimate stress. This is this maximum load it can resist. That is known as ultimate stress. So the tensor is reached at this point. Okay, of the breaking point, rupture point, which specimen fails break into 2. So this is breaking. So this is the ultimate stress from here when load is given here. So that will break it out. So this will break it. It will happen some breaking. Okay. So this is known as the breaking point or rupture. In these conditions, the material rupture. Next, the relation between the elastic model. Okay. So we Young's modulus, bulk modulus, and rigidity modulus. So E is known as modulus of elasticity, G is equal to modulus of rigidity, and K is equal to, that is, bulk modulus. So E is equal to 2G1 plus mu. So E is equal to 2N. N also rigidity one is G. Or mu is equal to 1 by M. That is known as the Poisson's ratio 1 by M. So mostly they have said G and mu. It may sometimes they use the notation N or 1 by M. E is equal to 3K. K is for bulk modulus 1 minus 2 by mu by 2K. So E is equal to 9 kg 3K plus G. And for these three equations are used, the relation between elastic model. And mu is equal to 3K minus 2G or 6K minus 2G. This is also, we can find the mu Poisson's ratio. So this is another one special formula, 3K minus 2G, 6K minus 2G. E is equal to modulus of elasticity and G is equal to modulus of rigidity, and K is equal to bulk modulus. And for isotropic materials, that kgs, so this value will be intermediate. So these values are very, very intermediate here. So mu value is 1 by 3, then E is equal to greater than, Young's modulus is greater than bulk modulus K. Then mu value is 1 by 3, less than 1 by 3. So if mu is equal to 1 by 3, 0.33 something it will be, I think the value is here. If mu is equal to reduce less than 1 by 3, then Young's modulus is greater than bulk modulus. And if mu is equal to 1 by 3, Young's modulus is equal to K, that is bulk modulus. If mu is equal to 1 by 3, E is less than K, that mu is equal to the value of the Poisson's ratios. So Lobby's constant is here, E is equal to mu 1 plus mu, that is 1 minus 2 mu, is equal to 2, that is gu 1 minus 2u. So these are some of the relationships. So this relations, by keeping the relationship, if it is Young's modulus or rigidity modulus, that value you can find it. Suppose if it is Young's modulus is known and the Poisson ratio is known, you can get the rigidity modulus and you can get the bulk modulus. By using this, you can get that kg value is known and you can get the value of A like that. So sometime on assuming the mu can be assumed 0.22 or 0.32, the mu value 1 by m value can be assumed, and also that can be substituted and you can get the value. Most of the Young's modulus values 2 into 10 power 5 Newton per mm square. So in some cases you know the mu values and E values, you can get the G values. So and by using this E is equal to 9 kg 3k plus n. So this relations is among 3, that is Young's modulus, and also that is known as the rigidity modulus, and also this K bulk modulus. So these relations are very important here. And by keeping these two values, K value and G value, so you can get the Poisson's ratios. So this when it is substituted, you will have the Poisson's ratio. By using the Poisson's ratio, you can verify the whether it is the value is correct or not. And we go for this isentropic materials. These points also very important. Okay, we are going to deal with the problems on the Young's modulus, bulk modulus, rigidity modulus. When a laboratory tensile test is conducted and Young's modulus of the material is found to be 2 into 10 power 5, 2.1 10 power 5 Newton per mm square. On the same material, torsion test is conducted and modulus of rigidity is found to be 0.78 10 power Newton per mm square. Determine the Poisson's ratio and bulk modulus of the materials. They ask the Poisson's ratio and bulk modulus. So Young's modulus is there, and also that n value rigidity modulus is there. E is equal to g1 plus mu is there. So you are going to substitute this Young's modulus value, E value here, and also that 2 and G value we are substituting here, and also 10 power 5 and also 1 plus mu. So you can get the mu value. Mu is equal to 0.346. This value is between 0.32 to 0.22 to 0.3. Okay, so this value is correct only for Poisson's ratio. From relationship E is equal to 3 1 minus 2 mu, you are going to substitute that E value 2.1 into 10 power 5 and 3. What is the K value we are going to determine here? They ask for the bulk modulus K, and 1 minus 2 into 0.346. So we put the value, substitute value here, and K is equal to 2.275 into 10 power 5 Newton per mm square. Okay, so in this we have used two formulas. Okay, they given the materials Young's modulus value and also the rigidity modulus values. By keeping this, we have determined the Poisson's ratio and also the bulk modulus of the materials. Okay. Material has modulus of rigidity equal to 0.4 into 10 power 5 Newton per mm square, and bulk modulus equal to 0.8 into 10 power 5 Newton per mm square. Find its Young's modulus and Poisson's ratios as. So the modulus, that is modulus of rigidity is 0.4, and this one is the bulk modulus is equal to 0.8 10 power 5 Newton per square. So find Young's modulus and Poisson's Young's modulus E value, and also you are going to find the mu value. How you are going to get the mu value here? And you are taking the relations E is equal to 9gk by 3k plus g. What is this 9? The 9 value is here, and also G 0.4 into 10 power 5, and you are substituted here, and the K value 0.8 into 10 power 5. We have substituted this both value 0.4 and 0.8 here, and also 3 and 0.8 into 10 power 5, and also 0.4 to 10 power 5. So finally we get the Young's modulus value 1.0286 into 10 power 5. So that is Newton per mm square. Young's modulus is equal to not Newton per mm square. It will come. So mm square is missing here. So we have to add it. And E is equal to 2g1 plus mu. Young's modulus 1.0286 in 10 power 5. and 2 into 0.4 into 10 power 5 and 1 plus mu. So we are going to we are applying this E is equal to 2 to 1 plus mu, and by applying this value here, so we put 1.028 10 power 5, 2 into 10 power 0.4 into 10 power 5 mu. So 1.2 by multiplying all this, you will get 1.2857 is equal to 1 plus mu is equal to 0.2857. This is mostly we go for 0.22 to 0.35. We go for this Poisson's ratio. That is the value is correct because 0.2857 is equal to between 0.22 to 0.35. So this is one of the best values. So we have found the Young's modulus and also the Poisson's ratio values. Okay, next problem. So next we go for in an experiment a bar of 30 mm diameter subjected to a pull of 60. The measured extensions on gauge length is 200 mm is 0.09 and the change in diameter is 0.6. Calculate the Poisson's ratio and the three models. Okay, they have given the diameter of the bar is there. Okay, then diameter of bar D is equal to 30, length of the bar L is equal to 200 and extension that is DL change in length and change in dia 0.039 and the pull is 60 kilonewtons, 60 into 30 10 cube newtons. So these are the values given. Calculate Poisson's ratio, that is mu or 1 by m, and the value of three model E, N and K. Okay, so first we go for the linear strain, that is known as linear strain, that is change length by original length. So 0.09 by 200. So you get the linear strain. So lateral strain is equal to delta D by D. So change in diameter is 0.039, change in length is 0.09. We have substituted that. Okay, and you get the 0.09 200 4.10 power minus 4, change in diameter to original diameter 1.3 into 10 power minus 4. The 1 by m, so we got the lateral strain by linear strain is equal to Poisson's ratio. So that is 1.3 into 10 power minus 4, 4.5 10 power minus. This 1 by m value is equal to 0.289. So the Poisson's ratio value is correct. So next we are going to find the three models. What are the models here? That is change in length delta is equal to PL by AE. So already we have seen change in length is equal to that is load P, load into length and area into Young's modulus. Okay, now you can subchange here the values here because first we have found the 1 by m is there, delta L values all here, delta L by L, delta D by D values here. So delta L values we have seen, we got the L values, then E is equal to PL by A delta L. Okay, the area is equal to pi d square by 4 because it is a circular bar. The pi into diameter 30 square by 4, 706.86 by mm square. So this is known as the value of area. And next we go for that the Young's modulus value. E is equal to that is P. What is the load? The load value is equal to 60 kilonewton, 60 into 10 cube. So the load value is 60 into 10 cubes, and length is equal to 200, and also the area we have found the area that is 0.09. So this is the length is equal to 200. So 706.86 into 0.09. So this is known as 1.8 into 10 power 5 or 188.6 to 8.08 Newton per mm square. So this is the unit is Newton per mm square. We got the value of Young's modulus. Next, bulk modulus. This is bulk modulus K is equal to E divided by 3 into 1 minus 2 by m. So we put the 3 value here. E value 188.6 to 8.08 and also 1 minus 2 by m. 2 by m means 2 into 1 by m. This value 2 will become into 1 by m. 1 by m, that is 1 by m value is known as, this is 1 by m value is 0.289. So this 1 by m value we are going to substitute. 2 into 1 by m, that is 2 by m. So 2 into 0.289 we are going to substitute here and we are getting the value that is 1.4, that is 10 power 5 or 1489 and 5.3 Newton per mm square. So this is known as this values for the bulk modulus. And when we can go for the rigidity modulus G. G is equal to E by 2 into 1 plus 1 by m. So by this value, by the formula of we are going to find the this rigidity modulus. Okay, so by the rigidity model you are getting the G value. So by the previous formula you will find that E value, you substitute the E value here, this value here, and 2 into 1 plus 1 by m. 1 by m value is equal to 0.289, and you substitute here and you get 7316.38 Newton per mm square. This is known as the value is known as the rigidity modulus. So 3 values we have determined here. So first we have found the 1 by m value 0.289, and we have found the Young's modulus, and again we got the bulk modulus, and finally we got the rigidity modulus. And next, a bore of cross section 8 mm into 8 mm is subject to an axial pull of 7,000 newtons. The lateral dimensions of the bore is found to be changed to 7.9985 mm into 7.985 mm. If the modulus of rigidity of material is 0.8 into 10 power 5 Newton mm square, determine the Poisson's ratio and modulus of elasticity. So first they used to find the Poisson's ratio and also modulus of elasticity. So area of section is equal to 8 into 8 64. So this is length into breadth, so length into length like that, 64 square. Axial pull is P is equal to 7,000 newtons, and lateral dimension is equal to this area. So this will be, when you multiply this, you get the area. And modulus of rigidity is equal to G is equal to 0.8 into 10 power 5 Newton per mm square. So let 1 by m is equal to the Poisson's ratio. So 1 by m is equal to Poisson's ratio. E is equal to modulus of elasticity or Young's modulus. So this two we have to find here. What is lateral strain is equal to change in lateral dimension to the original dimensions. Change in lateral dimensions. The lateral dimensions will be less. What is the change in lateral dimensions? Lateral dimension is 7.9985. So this is the original dimension is 8. That lateral dimensions is 7.8. So there happens some variations. 8 minus 7.9985. So 8 minus 7.985, 0.0015. That is original lateral dimension is 8. So when you divide this, then you will get the lateral strain. Okay, lateral strain. So axial stress is equal to load by area. The load is equal to 7,000. The area 8 into 8 64. So we have substituted this area here. That is sigma is equal to P by A. That is 7,000 divided by 64, 109.375 Newton per mm square. Okay, but lateral strain is equal to sigma by ME. So lateral strain is equal to, we go for that is stress and also that Young's modulus ME. This is one formula for finding only the lateral strains. So by this formula, the lateral strain values you can put here, and also that that's axial stress value 109.35, M value and E value will be there. So we are going to find this M value, E value. So this will be substituted here. 0.00, this is lateral strain will be substituted here. And ME is equal to, when you divide this, you will get this value here. That ME, we got the value of ME is equal to 2G 1 plus mu. So E is equal to 2G 1 plus mu. Instead of mu, you can put 1 by m. So this 1 by m Poisson's ratio is equal to mu. And also again you are going to substitute this and your m plus 1 by m, 2G m plus by m, and also ME is equal to 2G m plus 1. And this m can be cross multiplied, and you can bring this. So 583333 5833.33 is equal to 2 into 0.8 into 10 power 5. This is m plus 1. So you are substituting this value. So this value ME is equal to value. We are substituting here this value ME and 2G into m plus 1. So m plus 1 is equal to this value here you take, and also divide by 2 into 0.8 10 power 5. So m plus 1 is equal to 3.6458, and m is equal to 3.6458 minus 1. So the m value is 2.6458. So generally we are getting the m value. So but the Poisson's ratio is 1 by m. So 1 by m is equal to Poisson's ratio. So after getting m value, you divide 1 by m, that is 1 by 2.6458 is equal to 0.378. So it is under the value is a valuable value. So the values between 0.22 to 0.32 or 0.4, like that. So 0.3, so the Poisson's ratio value is 0.378. Substitute the value of m in equation 1 we get. So substitute the value of m in equation 1. So substitute the value of 0.1 equation 1, you will be getting that E is equal to 58333 or 0.33, that is E is equal to, you will get 2.6458. okay, this value can be, you can substitute this 1 by value in the equations, and 2.64 E is equal to, that is 5833.33, and you get the Young's model. E is equal to 2.2047 into 10 power 5. okay, and first we go for the Poisson's ratio and modulus of elasticity. So we have found here, so they have given some values, and at last we have find the two values. The Poisson's ratio is equal to 0.378 and the Young's modulus is 2.2047 into 10 power 5 Newton per mm square. Okay, by using these three formulas, that is very important to use these three formula in any cases. So Young's modulus or bulk modulus or rigidity modulus. So we have seen that the Young's, about the problems of the Young's modulus, bulk modulus and rigidity modulus. So in these cases you can find the Young's modulus, bulk modulus, rigidity modulus and Poisson's ratio, lateral strain and linear strains. These are very important. In some cases they will give the lateral strains and linear strains values. You can find some modulus values also. Sometimes they will give two modulus, Young's modulus or bulk modulus. You can find the rigidity modulus. So mostly in these cases the lateral strain and linear strains and the Poisson's ratio are very important. By keeping this, by analyzing the Young's modulus, bulk modulus and rigidity modulus, you can solve the problems. So the basics idea about the strains and the elasticity constants and the properties of materials are very important for the in the engineering area. So I thank every individuals for watching this video. Thank you.